Section 1.7 discusses regular graphs. And a regular graph is just a particular kind of graph where the degree of every vertex is the same. So if the degree of every vertex is equal to k for some integer k, then we would call that graph a k-regular graph, or sometimes we'll call it the graph regular of degree k. So we saw some examples in the warm-up. Another classic example of a three-regular graph is the Peterson graph. This graph pops up in a lot of different examples in graph theory. It looks sort of like a pentagon or a 5-cycle with another 5-cycle around the outside, and the vertices paired up like this. And we can see that the degree of every vertex is 3, right? 3, 3, etc. And so every single vertex is degree 3. So this is a three-regular graph of order 10 because there's 10 vertices. It's not the only three-regular graph. There's certainly many others. For example, if you have this graph, sometimes called a tetrahedron, or sometimes called a wheel graph with 3 spokes. This is another three-regular graph. We can see every vertex has degree 3. Oh, I guess it's also called K4. It's a complete graph on 4 vertices. Something like this would also be a complete graph, let's say, or sorry, not a complete graph, a regular graph of degree 3. You can check and make sure that every vertex has degree 3. So this would be a three-regular graph of degree 4, and this is, or sorry, a three-regular graph of order 4, because there's 4 vertices. This is a three-regular graph of order 6, etc. Okay, so clearly there's going to be different k-regular graphs of varying orders. And there's a couple of quick results that are pretty easy to prove. Every cycle graph, Cn, is going to be 2-regular, right? This is pretty clear to see. This is C3, this is C4, this is C5. Just sort of by the definition of this graph, it's pretty clear that it's going to be 2-regular, that every vertex has degree 2. We have the null graph. Remember, a null graph is just a graph that has no edges at all. So a null graph, which we might describe as big N sub little n, is 0-regular for all n. Right, here's big N sub 1, here's big N sub 2, here's big N sub 3. Every vertex has degree 0, so these graphs are 0-regular. And the third claim we have that if you have a k-regular graph of order n for some k, we don't know what k is necessarily, you can actually find the size of that graph. You can find the number of edges of that graph just sort of by thinking through what it should be. So let's look up this example. Let's look at the Peterson graph maybe. Every vertex has degree 3, which means if we're to sum up the degrees of all the vertices of the graph, we'll have 3 plus 3 plus 3 plus 3 plus 3, and then again 3 plus 3 plus 3 plus 3 plus 3. Well, there's 10 vertices, they all have degree 3, and so you get 30. But remember, the number of edges here is just going to be 15, right? 5 along the outside, 5 on this inner star, and then 5 connecting them. So this is 15, the number of edges, times 2. And we've seen in the last 2 sections that this always happens. If you add up the degrees of all the vertices, you're going to end up getting twice the number of edges. And so since 2 times the number of edges is going to be equal to the sum of the degrees of all the vertices, and we know that the degree of every vertex is k, so we're adding up a bunch of k's here. In particular, we're adding up exactly n k's. You get that the size is going to be n times k divided by 2. Just solving this equation for epsilon for the size of the graph, you get that the size of the graph has to be nk over 2, which actually allows you to prove something that we had already shown in a separate video, which is, or maybe, okay, so it gets at an idea that we saw in another video, but also gets at an idea from the warm-up, which is that if n is odd and k is odd, this equation is not going to make any sense because an odd number times an odd number is odd, and an odd number divided by 2 is not going to give you a whole number here. So it's really impossible to have a k-regular graph of order n if k and n are both odd. In other words, at least one of these, n and k, n or k, needs to be even. Okay, and so we've seen some different examples of various 2 regular graphs, and we've seen some examples of various 3 regular graphs up here, examples of 0 regular graphs. But is it possible that there's different k regular graphs that have the same order? In other words, if we fix k and we fix n for some particular k and n, could you come up with different examples of k regular graphs of order n? And, well, to some extent, it's hard to really talk about this without talking about what it means for graphs to be different. Like, certainly, you know, we could take this triangle and we could label its vertices A, B, and C, and we have a 2 regular graph of order 3, or if maybe we labeled them X, Y, and Z, you might argue this is a different graph, but structurally it's sort of the same. So we don't really want to think about these as 2 different graphs, it's just sort of renamed versions of the same graph. And so it's worth kind of thinking about, we'll come back to the idea of what does it mean for 2 graphs to be structurally different or structurally the same. But if we just let k equal 2, we can find examples of 2 graphs that are definitely different from each other that are both k regular. Now, in this case, k is equal to 2. So for orders that are small, it seems like maybe, let's see. I think for n equals 3, this is going to be our only 2 regular graph. You can play around with it and see if that's correct. For n equals 4, I think our only 2 regular graph is this cycle graph. For n equals 5, I think our only 2 regular graph would be C5. But when n is equal to 6, I claim there's actually 2 different 2 regular graphs of order 6. One, of course, would be the cycle graph of order 6. Let's see, 1, 2, 3, 4, 5, 6. Okay? But we could also have this disconnected graph, which is also 2 regular. These are clearly different graphs from each other since one's connected and the other is not connected, but they're both order 6, they both have 6 vertices, and they're both 2 regular because in both of these graphs, every vertex has degree 2. So it is possible to have different k-regular graphs of some fixed order. And you might be exploring that a little bit more in the exercises, but it's sort of an interesting question just in general in graph theory. How many different k-regular graphs do you have for a particular order?